Hi, this is a video in which we're going to discuss applications of Extrema. In other words, when you use the calculus process to find a minimum or a maximum value, how do you apply that to a word problem or a real-world application? Let's review with the process for solving an applied Extrema problem. The first thing we want to do is we want to read the problem carefully and make sure you understand what's being given to you and what it is you're trying to find out. If it's possible, if it's an actual three-dimensional problem, so to speak, make a sketch, okay, and label the parts. Decide on what variable you want to maximize or minimize, and if you have an equation that relates the variables in the problem together, make sure that you only have one variable in your equation. So you might have to solve for one variable in terms of another in order to do this. Find the domain of the function. Now this is a practical domain. Okay, so mathematically your domain might be all real numbers, but if you're talking about lengths of the sides of a field, you can't exactly have negative lengths, and even a zero length might be a lower bound. So find out what the practical values of your independent variable would be. Then here's finally we're at a calculus step with number 5. Find the critical points of the function you came up with, okay, to relate the quantities in the problem. If the domain is a closed interval, you want to evaluate the function at the endpoints and at each critical number to see which of those yields an absolute maximum or minimum. And if the domain is an open interval, you've got the critical point theorem. If you've only got one critical number, you're going to apply that. And if you have more than one critical number, you have to evaluate the function at the critical numbers and then find out what happens as the function approaches the x values that are your endpoints to see if an absolute maximum or minimum exists at one of the critical points. So let's take a look at some examples of how to apply these steps to finding Extrema. Okay, in this example, we have a student who's participating in what's called an orienteering challenge. This is a challenge that's very similar to the modern geocaching, where you try to get to a location in the real world as fast as possible to find clues or objects. So the student has to get to a specific tree in the woods as fast as he or she can. He can get there by traveling east along a trail for 300 meters, and then north through the woods for 800 meters. The problem with this is he can run a lot faster on the trail than he can through the woods. He can run at 160 meters per minute along the trail, but only 70 meters per minute through the woods. So what he's wondering is there a combination of paths along the trail and through the woods that would get him to the tree in a minimum amount of time? So the first thing we have to do, since this is a real-world physical situation, let's draw a picture, okay? So here's our student over here. We know he's 300 meters on the trail. This horizontal line is the trail, okay? The vertical line is a path through the woods, and this is the tree, okay? So he's 300 meters here away from where he would turn and run north to the tree in the woods. What we want to know is there some variable x, is there some value of x here that is the point where he should break off running on the trail and run through the woods? Okay, so let's set things up a little. We know that if the whole distance to this turning point is 300 meters, and this part is x, this part is 300 minus x. Okay, so 300 minus x plus x gives me the total length of the trail to the turning point. That's 300 meters. This is given as 800 meters. And what you want to realize is you've got a right triangle here. This is a right angle. And we know the Pythagorean theorem gives us a relationship among the sides of a right triangle. Okay, this hypotenuse expression comes from the Pythagorean theorem, a squared plus b squared equals c squared. So how did I get this? I took x squared, 800 squared, added them together, and then took the square root to get the value of c. We want to minimize time, but all of these expressions involve distance. Okay, so how do we relate distance and time? You might remember the distance is your speed times the time you're traveling at that speed, right? So I can travel, if I'm traveling at, say, 60 miles an hour, and I want to go 300 miles, how long would it take me to get there? Well, I take my distance 300, okay, and I divide by my speed 60, it's going to take me 5 hours to make that trip, okay? So if I solve this equation for time, I get time as distance divided by speed. The total time the student will take on the optimal path is along the orange line in the diagram, right? So part of the way across the trail and then part of the way through the woods. Just remember, he's traveling faster on the trail and slower through the woods. So let's see if we can come up with an equation for that. So the total time is going to be his distance along the trail, okay, divided by his speed on the trail. Remember, these are both, this is in meters and this is meters per minute, okay, so this tells how many minutes he's going to run on the trail. Okay, it's distance divided by speed. Here is the time he's spending running through the woods. This is the distance along the hypotenuse of that right triangle. Okay, and if he can run only at 70 meters per minute in the woods. So this term is an expression for the time he's spending running through the woods. His total time to get to the tree is time on the trail plus time in the woods. Now let's talk about the domain of x. X, if you recall, is this distance, okay, that is the distance between the original turning off point and the point where he's going to turn and actually run through the woods, okay? So what would make sense for x values? You can imagine if we slid this hypotenuse all the way over to the right angle, x would be 0, and our student would run 300 meters on the trail, 800 meters through the woods. Okay, that's kind of the smallest x. What's the largest x? Well, suppose we move the end of the triangle out all the way to where the student currently is. Then x is 300 meters, and that would mean the student doesn't run on the trail at all, but originally just starts out running right through the woods to the tree. So again, we can see reasonable values of x are from 0, including 0, up to 300. Negative distances don't make sense, okay? So basically, if x is greater than 300, the triangle we drew wouldn't make sense. It wouldn't be the one we drew. Okay, so we have our big time function, t of x, and we need to differentiate that with respect to x, okay, to find critical points. But let's simplify it a little, okay? If you take a look at the original function here, okay, I can write both of the terms in the numerator here, 300 and negative x over 160. And that should simplify things a little. I'm also going to pull out the denominators, and I'm going to basically write this as 1/70th times this. That way I can pull it through the differentiation. Okay? So here's a little bit of algebra simplification. 300 divided by 160 is 15/8. Okay? This x divided by 160 is going to be negative 1/60th x. And like I said, I'm just going to pull out the divide by 70 that was in the denominator and make that 1/70th times this quantity. I'm also rewriting my square root as this expression to the 1/2 power. The reason for doing all of these operations algebraically is that the algebra in advance makes it a lot easier to do calculus with the power rule. So let's now actually take the derivative. The derivative of 15/8, it's a constant, is 0, so that drops out of the derivative. And then I have negative 1/60th x, and again, when I take the derivative of this term, I just get the negative 1/60th. This is a coefficient. I'm just going to pull it out in front and deal with it later when I do my algebraic simplifying. This expression is a function composition. Okay, I've got this inside, and the whole thing is a square root. so I need to use the chain rule on it. First, I'm going to take the derivative of the outside function. I'm going to bring down my 1/2, rewrite what's in the parentheses, drop the exponent by 1, then multiply that by the derivative of what's inside. 800 squared is just a number, so its derivative, since it's a constant, is 0, and x squared is what gives me the 2x. Now that we're done with the calculus, let's do some more algebra to simplify. Not much I can do with -1/60th, but again, if you take a look over here, notice I've got a 2 on the bottom here, and then a 2x over here. So these 2's divide out, and I'm left with x in the numerator, a 70 in the denominator, and this expression is actually in the denominator because of the negative sign on the exponent, and it's a square root. So this is the simplified version of my derivative. Next thing, in order to find the critical numbers, I need to set this derivative equal to 0 and solve for x. So I'm making t prime of x 0. And then I need to do some algebra to solve for x. So the first thing I'm going to do is add 1/60th to both sides, and it winds up on the other side with a positive sign. And then you might notice it's a proportion. I have one fraction here and another fraction here. So I can just cross multiply to solve. This gives me 160x on one side and 1 times this quantity in the denominator on the other side. You might recognize that I can divide out a 10 from both of these expressions, giving me 16x equals 7 times the square root. Okay. I want to eventually get the x out of the square root, so I'm going to square both sides. Okay, 16x, the whole thing squared is 256x squared. Remember, if you square the right side, you not only square the square root, but you have to square the constant outside. Okay, next I'm going to distribute my 49. And you'll notice I get 49 times 800 squared. This is a huge number, and I don't really want to deal with it just now. That's how come I'm not simplifying it. Okay. But you can see I did get a 49x squared. So what I'm going to do is subtract 49x squared from both sides, which gives me 207x squared equals this big enormous number. Okay? Divide both sides by 207, and I'm finally to the point where I can take the square root of both sides. Let's do a little thinking first. 49 is a perfect square. Its square is 7. 800 squared, the square root of that is 800. So I get 7 times 800 over the square root of 207. Now I can break out my calculator and evaluate this, and I get about 389. Okay, so if you remember, our domain for x went from 0 to 300, so this value isn't in the domain. So we have a closed interval for our domain, okay? That means our minimum time has to occur at one of the endpoints, okay? So in other words, this critical number is not in the domain, so we're not using it. Now I have to focus on the endpoints of my intervals. Those were 0 and 300. So remember how you do this. You go back to the time function, not the derivative of it, but the time function, and you plug in these x values, okay? So I'm evaluating here t of 0. That gives me 13.3 minutes. Okay, this means when x is 0, our student would run 300 meters along the trail, then make a left and go 800 meters through the woods. That takes him 13.3 minutes. If t is 300, that's the situation where our runner is going to just immediately break off and run through the woods. He's not going to spend any time on the trail. And you can see when we plug in 300 for x here, we get a time of 12.2 minutes. That means that his time is minimized when the student heads straight for the tree through the forest and doesn't run on the trail at all. Okay, so this example is showing you how to do an applied maximum problem when you've got a closed interval and the critical number that you got out of the calculus is not actually in your practical domain. So now you have to check both endpoints of your interval. Let's take a look at another type of example. This is really common for applied extrema type problems. Suppose you're manufacturing an open box. That means a box without a lid. And it's going to be made by cutting a square from each corner of a 12 by 12 inch piece of metal. So you've got a square foot piece of metal, and you want to then cut a little square out of each corner that's the same length on each sides, and you want to fold up the sides. So what size square should you cut from the corners to maximize the volume of the box? Well, this is another situation where a diagram helps. Okay, so here is our piece of metal. These shaded squares in the corner are the unknown x by x squares. This is what we're trying to find out, is what is x, okay? So how much should I cut out of each corner here so I can fold the box up? Now the important thing to realize was your original length and your original width was 12 inches. If you cut two x-sized inch-sized squares out, okay, what's left is going to be your original 12 inches minus x minus another x. So this length is now 12 minus 2x. Your original piece of metal was a square, so the same thing is true of your width. When you fold up the edges of the box, it's going to look like this. Okay, its length will be 12 minus 2x, its width will be 12 minus 2x, and this is the little x-inch corner flap that you're going to fold up. So I have a length, a width, and a height. Okay, now you've got to try to figure out what are reasonable values for x. Okay, the smallest value x can be a 0. Okay, if you didn't cut anything out of the corner, and then you'd be just left with a flat piece of metal you can't fold up. If you think about the largest value of x, okay, if x was half the width of the box, like 6 inches, you would wind up cutting away the entire box, okay? And there would be pretty much no box left, okay? We know that the width and the length can't be negative, so we can't let anything become a negative number. So it looks like x is trapped between 0 and 6. That's our practical domain. The volume, you have to remember how to find a volume of a box, and that's its length times its width times its height. If you multiply all of these expressions together, you can use FOIL on this and then distribute an x. You get 144x minus 48x squared plus 4x cubed. Okay, so this is our expression for volume. This is the thing we want to maximize. So we're going to take the derivative and set it to 0. Okay, derivative of the first term is 144. 2 times 48 is negative 96, and drop the exponent by 1, and 4 times 3 is 12x squared. Okay, each one of these terms is a multiple of 12, so let me divide out a 12 to make things easy. Once I divide out a 12, I notice this is probably factorable. Okay, I'm looking for two numbers that multiply to give me 12 and add to give me negative 8. That would be negative 6 and negative 2. So here's the way the derivative factors. Remember, the 12 is not going to give you any values for x because there's no variable out here, but I'm going to set the x minus 6 and the x minus 2 to 0 and solve for critical numbers. Okay, I've gotten two critical numbers, 6, which if you remember is one of my domain's endpoints, and 2, which is inside the practical domain. So since we have a closed interval for the domain, I have to evaluate the volume function not only at the critical numbers but also the endpoints of the domain. But again, one of these critical numbers happened at one of the endpoints. So here is the volume function evaluated at 0. No surprise there. Remember, I said if I don't cut anything out of the corners, I have no box. The volume is 0. And we also said at 6, we'd cut away the entire box, which means I'd also have no box. The volume is 0. Which means my maximum volume occurs when x is 2 inches. And what is the maximum volume? It's 128 cubic inches. Here is one last example, okay? And this is one where epidemiologists have discovered a communicable disease running through State College, Pennsylvania, and they estimate that T days after the disease is first observed, the percent of the population infected is given by this equation. Okay, so here T is the number of days since the disease was first observed. P of T is a percentage of the population that's infected. And we're being told the domain of T. Okay, so T goes from 0 days out to 20 days. It's possible that this communicable disease only has a 20-day course. So they want to know, after how many days is the percent of the population infected a maximum? And what is that maximum percent? This is something epidemiologists do a lot whenever they're confronted with any kind of an infection. They want to know when the disease is going to peak, and they need to do that. They need to know that so that they are sure they have enough resources, enough manpower on hand to handle the peak. So let's first rewrite P of T, okay, and we're going to do that by bringing out the 1,000 in the denominator. We're going to write that as 1/1000th as a coefficient. That just makes it easier to do calculus. We're going to take the derivative on this, okay, we'll bring the constant through and then use the power rule here. 3 times 20, t is 60t squared, and 4 times t to the 4th, 4t cubed. Then we're going to set it equal to 0. Multiply both sides by 1,000 to get rid of this coefficient. Well, one good thing about multiplying by 0 is it eats whatever you throw at it, so 1,000 times 0 is still 1,000. And I'm left with this expression here. I'm going to factor out a 4t squared. That's my greatest common factor. And then I am going to be setting each of these factors equal to 0. Okay, when 4t squared is 0, t is 0. When 15 minus t is equal to 0, t is 15. If you remember, the domain was a closed interval, so I need to check these critical values and the endpoints for a maximum. Okay, so essentially this t0 is one of our endpoints. So I only have 3 critical numbers to check. I am going to evaluate p at 0, at 15, and at 20. You can see when I plug in 0, this is 0 days, okay? Nobody's infected because we haven't observed the infection yet. And at 20 days, when I plug in 20, 0% of the population is infected because the disease has run its course in 20 days. When I plug in 15, though, I get 16.875. Okay? And what does that mean? If you remember, P of T returns a percentage. So this is the maximum percent of people in the population infected. It's 16.875%, and it happens 15 days after the disease is first observed. And this is a small example of different ways to solve applied extrema problems.